Okay, so if you notice in the notes, the lecture notes, I have this question here. So this question is very good in order for me to explain all the elements that you probably will need when you answer this kind of questions for bending stress. Okay, so these questions indicated given to you a cantilever beam. A cantilever beam with a cross-sectional area that you can see here. So this is a composite shape. In this figure that you can see, this beam is being subjected to a concentrated moment at its free end. So you are required to answer some questions related to this beam. So what you can see is that this beam only being subjected to 100 kilonewton meter moment, anti-clockwise moment at one end, at its free end. And the other end, it was supported by a fixed support. And you can see that the cross-sectional area here is a rectangle with another rectangle hole being drilled out of this shape. So obviously, if we are needing to answer these questions, if you are asked the questions to find bending stress, then we need to find the locations of the neutral axis. So that is the most important thing. But before we go further in finding the neutral axis, what do we need to do first? The first thing that we need to do is to find the support reaction at that fixed support. Okay. All right. So the part A of these questions asks you to calculate the reaction at the support. So if we needed to find the reaction support, what do we need to do first? Come on, give me the answer in the chat box. What do we need to do first if we need to find the reaction support? We draw the free body diagram. Very good. So we draw the free body diagram. Take that beam, separate it from the rest of the world, and draw its free body diagram. So we know that this is a fixed support. So the fixed support reaction will prevent it from moving in the X, in the Y direction, and also prevent it from rotating. So we draw the free body diagram. So this is my free body diagram. And I have that moment, concentrated moment, being applied at one end, at the free end of this fixed support. And I will reveal my support reaction. I have it will prevent it from moving. The fixed support will prevent it from moving upward. It will prevent it from moving to the left and right. It will also prevent it from rotating. So now we need to find all this reaction support. We need to find SY, MS, and SX. So what do we use? We use static equilibrium equation. So we need that static equilibrium equation to sum forces in X and Y direction. And also for moment, for point at point S. So I use static equilibrium equation. First thing I do, sum moment as sum forces in Y direction. So as you can see, there's no external applied force that's going upward. So my Sy here would be equals to 0. So this moment reaction, the moment external concentrated moment, is not going to cause it to go up and down. It's just going to cause it to rotate. And then to cause the moment at that point S there. And I do another one using static equilibrium equation. I sum forces in X direction. So the same thing happened here. There's no forces applied, external force applied in the X direction, to the left or to the right. So that reaction, that support, that fixed support is not going to react to that in that axis because there's no support reaction. There's no external force being applied. So it's not going to react by preventing from moving in X direction because there's no applied force in that direction. So that x is also equals to 0. And the next thing is that we need to solve for that moment. So for that at the support reaction. So the moment that we have in that fixed end pair. So we have we can now sum moment in at point A, and that must be all equals to 0. And we said that when I assemble my equation, I denote that going to anti-clockwise for my external moment is going to be equal to 0. It's going to be positive. That anti-clockwise is positive for my external moment. So now I sum all my moment. I have that concentrated moment, and I have, because I have concentrated moment applied to that free end, my reaction, my support is going to react from preventing that from going downward. It's going to anti-clockwise. So it's going to prevent it from, this is a fixed support, this is moment. So this support is going to want to prevent it from keep going that way. So what it will do, it will stop it from moving by reacting on the clockwise rotation. So I hope this is not a new concept. Yeah, everyone should now understand what I'm talking about. So this is my fixed support. I have concentrated moment. If I don't have support here, what's going to happen is that it's going to want to rotate. But because I have that support, what does that support do? It is stopping that from happening. So how to stop that from happening is by reacting, by rotating it to the clockwise rotation. So it is going to now become in equilibrium. So it's going to be in balance. So you sum all those moments, it's going to be equal to 0. So that ms now is equal to 100 kilonewton meter. So that ms, you can see that it's positive. I get it as a positive here. Okay, so it's positive. So what does that mean? My rotation here, my moment, the sign for my moment that I put here is correct. So that's going to be, that reaction will be, and it will be clockwise. So as you can see that what's happening here is that it is going to cause that beam to have a sad face, to have a frowny face, because it's going, the curvature now is going to look like this, what you can see, what I'm doing, and what also you see in that screen there. So it's a frowny face. So what does that mean? All the top part of that beam is going to be in tension because now it is experiencing elongation, but the top bit is experiencing compression. So that's going to be experiencing contraction, the one at the bottom. So when you do your calculation for your bending stress, if you are asked a distance from the neutral axis to the top of that neutral axis, you should get a positive. And if you are asked any distance from the neutral axis to the lower part, it should be negative because it is compression stress. So that's different if we have a smiley face. So when it's a smiley face, the compression happens at the top and the tension happens at the bottom. So always have something that's flexible with you to help and guide you to answer the question. Okay, so that's for the reaction support. So if you have calculated all this correctly, you show all the steps. Okay, so when you do, if you notice for the test one, okay, when we do all our free body diagram, you can see when you don't have your dimension, you did not get 100% of that. Okay, you will get half only. Why? It's because your dimension is not shown. So you please, when you draw free body diagram, have all of them, of all your dimension written or drawn in your free body diagram. Okay, and show all the steps. Even if you think that that step is not necessary for the answer, but if you think it will help you, just write down all the steps. Okay, so step 1, step 2, step 3, and so on. Okay, so all this, for this, are you guys clear? So what we are doing here is all external. It's not internal yet. This is an external force. Clear? Okay. Yang senyap-senyap, always very quiet in this class, please don't hesitate, answer when I ask. So I can move on, okay? All right, so this is all clear, yeah? And then you are asked here to draw shear force and the bending moment diagram. So what we need to do now is to draw our axis. So I have my axis for my shear force and my shear force and my bending moment diagram here. So this is a distance L. All right. So I have no other distributed load. I only have that concentrated load, a concentrated moment. So obviously, there's no force that is going to want to have this beam to shear. Okay, like if we have distributed force going downward, obviously there's going to be a shear force that's going to prevent it from being sheared. Okay, so it's like this. You see, you can see what I'm doing. Okay, so when we have distributed load or concentrated load, external pointing downward, there will be a shear force going upward. Or if we have a support, and if let's say we have a support reaction here that's going upward, obviously this beam is going, the internal shear force is going to be generated to prevent that. But because we don't have any of those, any distributed load, or it does not have any concentrated load acting downward or upward, there's not going to be any shear force generated, because the concentrated moment, as I said, is not going to try to move it upward and downward. So there's no force that is going to be reacted or generated on that beam for the internal shear force. So for the internal shear force, it is going to be 0. There's not going to be any shear force here. This is a case of pure bending. Okay, so it's just going to be moment that is going to be bending, internal bending moment that's going to be generated. Okay, so how do we draw the internal bending moment diagram? So first, remember when I introduced this expression. In the kitchen, the clock is up. The kitchen counter is below. Okay, so here, as you can see in this very small kitchen, the clock is up, located up at the top of the counter, and the kitchen counter is downward at the bottom. Okay, so remember that when you have an external concentrated moment on your load diagram, if it's showing going to the left, to the anti-clockwise, what does that mean is that in your bending moment diagram, for the internal bending moment diagram, this is going to cause this beam, the internal bending moment to go downward in the diagram. So that's going to cause it to go downward. The counterclockwise is going to cause internal moment to go downward. And that's going to be constant for the rest of the length of the beam, because as you can see, there's no more other concentrated load, a concentrated moment being applied throughout this beam. So that's going to be constant for each of this segment. If I do very small segment, I do all this method of section for very small element, I can reveal that the internal bending moment is negative 100 kilonewton meter. So that is what does this in the bending moment diagram is all about. And then you can see at the end, at L, at the end of that beam, there is a reaction force that we calculate just then. Okay, so that is 100 kilonewton meter. So that is your point in your load diagram. It is going clockwise. So when it's clockwise in your load diagram, in your bending moment diagram, it must go up. Okay, that shows that it is internal moment that is going to be generated there is going to be going upward. So that's positive 100 kilonewton meter. That's going upward. So that's going from negative 100 with plus 100. It's going to go back to 0. So this is my bending moment diagram. So this is where a lot of you don't understand. What does the one do you think that we're drawing, what we draw the shear force in the bending moment diagram here, is external. It is not external. Okay, you remember what you plot here is internal shear force and internal bending moment. So don't tell me that it's confusing now. I'm going to show it to you. If, let's say, everyone by now should remember that method of section. Okay, if every time you want to reveal the shear force and bending moment diagram, we do method of section. So that is what you learn from statics, what we have learned in chapter 1. So if, let's say, I take a very small element from the beginning of that beam, I cut it in that segment, and I draw the free body diagram of the segment on my left side. So this is my left section, okay? You saw that you have bending moment, you have concentrated moment being applied on that end of that beam. So that is counterclockwise. Okay, it is counterclockwise. So for external, counterclockwise is positive. Okay, if we sum moment in this at this point AA, okay, we sum moment at AA. So if we have this counterclockwise, the internal bending moment will try to prevent that from rotating. Okay, so that you will have MAA here going clockwise. Is this all clear to everyone? Okay, so we have this. With some moment, we will find that MAA, which is negative, is equals to plus 100 kilonewton meter for external. Okay, this is going to be positive. This is going to be negative. Equals to 0. So our MAA equals to 100 kilonewton meter. So that is what we calculate. This is our internal bending moment diagram. And why do we say this is as negative? Why do we draw it as negative? So imagine that that is going to be at this point. This is AA. Okay. Why do I say that is negative internal moment diagram? According to our sign convention that we set up in the first chapter, lesson 3. According to our sign convention, this is a negative internal bending moment. So if we go back to this, this is what you have in your chapter 1, lesson 3. Look at this. if we are taking the internal moment or force for the left side of the beam, this moment is positive. So when it's like that, it is negative. So in contrast, if we take it from this side, this is going to be positive and this is negative. So always go back to this sign convention. Okay, so this is internal moment diagram. This is internal bending moment that is positive. So when it is clockwise, it is going to be negative. So if we go back to what we have written here, if we have that we have calculated here, you see that this internal bending moment for this part is going clockwise. So that is going to be negative. So that's why when we plot it up down here, it is negative. If you do the same thing, but you start from here, you do method of section and that part, and we begin from this. We begin from the left end, okay? Oh no, let's forget about that. Now, if I draw my right section instead, okay, so I draw my right segment. So I draw this part. This is what I draw. According to Newton's third law, this one will go that way. Okay, it must be the same, but the same magnitude, but opposite direction. Okay, no, this one going this way. Okay, so as you can see, according to our sign convention that we set up just then, this is positive. Keliru sudah saya. All right, so this is positive going that way. Let's go back to see this one. Here it is. So I draw this part. So this is going to go that way. So this one is going this way. Okay, can you guys see this? So this is going this way. So according to our sign convention, that is negative. So no matter if you draw it on the left side or you draw it on the right side, it should give you the same bending moment diagram. But we are always going to start from the left side. So what we draw is actually the left side. If you imagine you are drawing that bending moment at this method of section, we draw that left side over and over and over and over again. So that's why we get that this one as negative. So what you draw here are all internal bending moment diagram, internal bending moment. Is this clear? I am not mad here. I'm just, I just want you guys to really grasp this idea. Okay? Because I have a lot of you ask me who think that what we draw is external. It is not external. It is internal. Okay? So always, I said, go back to your bending moment diagram, your sign convention, this part. Always go back here. Draw it in your sheets of paper and remember what all of this. Okay? So this is for internal forces. So when we said normal force, we said shear force, we said bending moment. It's all indicating that this is an internal forces and moment. Okay, so if that's clear, we can move on. Now let's move on to part C of this question. So part C of these questions asks you to determine the bending stress at point A, B, C, and D. So there is A, B, C, and D here. So as we have derived, when we want to when we want to determine the bending stress, we want to determine bending stress at any point, we can use flexure formula. So this is flexure formula that we have derived. I will use the one with the negative. I won't drop that negative because I notice a lot of you are not able to determine that, to visualize that compression and also that tension, the elongation and also the contraction. So I will not drop that negative. I'll keep that negative there. So this is what we derive. So we have M, which is the bending moment, internal bending moment, which we already determined. So when from our diagram here, we know the bending moment, internal bending moment along the beam. So at any location along the beam, we can use this bending moment diagram to determine what is our bending moment at any location of that beam. So that sort things out. We have our M, but we don't have our Y here. So Y here is the location of that A, B, C, and D from the neutral axis. So we don't know that yet because we don't know where exactly this neutral axis is located. We need to locate that neutral axis. And also we don't have I. So with I, we know that we need to use parallel axis theorem. So we need, in parallel axis theorem, there's a term of D in which it is the location from the distance from the neutral axis to the centroid of each of this composite shape, each of this regular shape in this composite shape. So in this regular shape, we have, in this composite shape, we have two shapes. We have a rectangle with a smaller dimension and a rectangle with a larger dimension. So we need to find the neutral axis first. So how do we do that? So I will define my reference point. So I will have my reference point as X and Y here. So axis X is at the base of that beam and axis Y is on the left extreme of that cross-sectional area. Okay, if you do it like this all the time, I can guarantee that you're not going to get it wrong. So determine your reference point first, the reference axis. This is my reference axis. So now I need to find the Y bar here. Y bar is the distance from the base of that beam to the neutral axis. So it will tell you the location or the location of the neutral axis from the bottom or the base of this beam. So I need to use this equation. So this equation is a sum of Y. The Y here, that for this equation, the Y here is the centroid of each of these segment, segment 1 and segment 2, and A is the area of each of these segment. So for shape 1, I denote the shape 1 as the bigger rectangle, and the shape 2 is the hole. The hole has a shape of a smaller rectangle. So that is what I define. So now I need to find the centroid for each of these segments. So for segment, the big one, the centroid will be located at the center of that shape. So here I have put that cross there. So that will be located at 125 millimeter from the base, from the reference point. So that is from the x-axis. So that is my centroid for my shape 1. The centroid for my shape 2 is located at the middle in the middle of that shape 2. And where is it located from the base of the beam? Of course, it's 50, half of its dimension, plus 20 here. So that's going to be 70. Now I will use my my table. I will list them out so that I clearly can see if I have done something wrong. Okay, so now I can see that the location of the centroid for each of the segment, I put it in one column. I have here For segment 1, it is, I've changed this to meter already. Okay, so all are in meter. So as you can see, I myself did mistake when I did not change the unit. So always trace or track your unit. When you do your unit, when you did not track your unit, you're always going to make mistake, like myself. Okay, and then you find the area. The area is the base times the height. So base times the height is the for the base of the bigger shape is 0.1 and the height is 0.25. So I get this one. And for the smaller rectangle, the hole here, it's 100 millimeter times 60 millimeter. 60 is from here to here. So that is, when I do that in meter, I get this as the area. And you must put negative here. Negative because we take that out, we drill that out. It is a hole. We need to take them out, so the negative must be subtracted from that area, the sum of that area. So this is the sum of this area, and you times it with the centroid location, you get this one. You times 0.07 times negative 0.06, you get this one. And then you need to sum them and you will get this. When you do that calculation correctly, you will get the location of your neutral axis. It is at 142.3 millimeter, but I have changed it to meter already. So this Y here, 142.3 millimeter. 0.2, 0.3, 0.4, it's not a problem. As long as it's within the range of plus minus of 0.1, it should be okay. Okay, so we get this. That's our neutral axis. Anyone have problem locating this neutral axis now? You can tell me, I can repeat this again. Tak ada masalah? All clear? Okay. All right. So don't hesitate. Okay. That's okay. All right. If you think that this is now okay, now we can proceed. Okay. Now we have determined our neutral axis. So we find out our neutral axis is located at 142.3 from the base of the materials. So we can now locate our Y. So for A, B, C, and D, that point A, B, C, and D, we can now get that distance. So any distance, we can get the Y in this equation, and this distance from the neutral, this is the distance from the neutral axis to the location of interest. For these particular questions, we have X, A, B, C, and D. So that is the location that we are interested in looking what is the bending stress at each of these locations. So now, because I use this bending stress equation that has the negative here, the one I extracted exactly how I derived them without dropping that negative. So when the Y that we are interested, the location that we are interested is above that neutral axis, I will denote that all the location above that neutral axis is going to be positive. And if I have the interested location that I want to say, the bending stress is below that neutral axis, I will denote that location as negative. That is what I am going to do when I am doing my calculation. Okay, so bear that in mind when you do this calculation on bending stress. So when Y is on the top, it's going to be positive. When the Y is at the bottom of the neutral axis, we are going to say that it is negative. So in a way, now your reference point is going to shift. So your reference point now for this y, the location of y, is going to be at that neutral axis. So your neutral axis is going to be 0. That is your reference point. And if we go up, it's positive. If we go down, that is negative. So let's sort that out. Now, what I need left to start calculating my bending stress is the I. That is the area moment of inertia. So I need to find I still need the I, and this is the area moment of inertia of the composite shaped beam, which can be determined using parallel axis theorem, this one here. And from here, we can find Ix. Ix is the area moment of inertia for the individual segment. And since this is rectangle, the Ix for rectangle is equals to a 12 of base times h cubed. So if you have other shape, you go and have a look at the table at the back of the book. So here is the book. This I show because I know a lot of you will make the same mistake over and over and over again. And then when I mark your answer, I'll be frustrated. So I want to show all of it to you. This is spoon fit already, okay? So this is the back of the book. You have all of them here. All right. So for all of the shapes, you have it here. And I also provide this in your notes. So don't tell me you don't know where to get it. All right. I might sound angry, but I'm not. I just need you guys to understand this. This topic is very interesting for me. So all of you must find it interesting as well. I do a lot of bending tests when I did my PhD. It reminds me of my time in my university. All right, so here that parallel axis theorem has two terms that you need to add them up. You need to do for each of the regular shape, and if it's being drilled out, it should be negative, and the one that stays is positive. So I have Ix for shape 1, and now I have this term here, D. What is D? D is the distance from the neutral axis to the centroid of the composite shape. So that is what D is all about. Okay, so we already determined what is our centroid for each of the segments from the very beginning when we try to find the neutral axis. So for the larger rectangle, this is where, let me begin. This is where our centroid located, that dot there. It's right in the middle of that. What is centroid actually? Centroid is where if you do that, if you put your hand, right, if that's rectangle, if you put your hand right in the middle of that beam, right in the middle of that centroid, it should not, it will be in balance. I don't know exactly where is that for my book, but it should be staying there. So it's like a center of the gravity. So that for this beam, that the shape of that beam, the centroid is right in the middle of that shape. So that the red color one is where the centroid of that big rectangle. And that is located 125 from the base of the beam. So D here is the distance from the neutral axis to that centroid. So this is what is this one. So when you do that calculation, later we'll do that calculation. For the smaller one, here, this is, you can see that cross in the middle of that beam. That's just in the middle of that shape. It's just to show you where exactly that centroid is going to be located. So what that distance is 70 from the base of the beam. So what is D? D here is from the neutral axis to the centroid. So we have D1 and D2 there. So how do we calculate that? It's easy. So now we have, and you can see that both are at the bottom of that beam. But for D, it does not really matter. So like I said, any distance from the neutral axis to downward, it's negative. From upward, from neutral axis upward, it's going to be positive. But for this case, it does not really matter because we are going to square them anyway. So if we have squaring negative number, it's going to be positive as well. So it does not matter if you put it as negative or positive here, because we are going to square them and it's going to become positive anyway. So for D here, D1 here, we will get 0.0173. That is 142.3 minus 125. You will get that as 17.3 millimeter. And that I convert it to meter, this is what I get. And for D2 is 142.3 minus 70, and you will get it as 72.3. Okay, so we are summing all of them. Now we can assemble our equation. So this is for shape 1. This is for shape 2. A 12 of 0.1, which is the base of that shape, that is from one end to another end. That's 100 millimeters, so 0.1 meter. And then we have the height. Height is the height, overall height. That's 0.25 cube. Plus the area. This is area. 0.1 times 0.25. This is D that we get here. So that's for shape 1. And for shape 2, we have 0.6. This is 0.6 here. Times 0.1 is its height. And we have this area of 2, 0.6 times 0.06 times 0.1, and this D is that distance that we have calculated just then. So when we do that calculation correctly, this is the I that we get. Now we have all of them. We have M, the one that we get from our bending moment diagram. We have Y is the location from the neutral axis to the A, B, C, D. And then we have the I that we have calculated. It's easy from here. It's be smooth sailing. We can start with bending stress at A. So what I'm going to do for myself, I'm going to draw that line. That line indicated where A is located. So I want to find out what's the stress. Now imagine back to the beam. This is our beam. We want to find out the stress at the top part of our beam. So when we determine our shape of this beam when it's being bended, when being applied by concentrated moment, we've already discovered that the top part is going to experience tension. That your answer now, if you use this bending stress equation, the formula, because we said this is in tension, your calculation should be positive for that part. Okay, so now let's have a look. Is it going to be positive? Okay, so I have my bending moment. Now I need to, let's have a look at Y first, okay? So Y is the distance from the neutral axis, the blue color line here, to the point of interest. So my point of interest is A, and that is 250. A is located on the top of that beam. The beam's height is 250, so that's 250 minus 143, 2.3, which is the location of the neutral axis from the reference point. So that is equals to 107.7. Yeah, so that's 107.7. I converted it to meter already here. Okay, so that's my Y. This is my Y, my M. You can see at any point of that beam, the bending moment is constant at negative 100 kilonewton meter. So I'm going to put that negative 100 kilonewton meter, which is my bending moment, internal bending moment, times that my Y, the distance from the neutral axis to A, and that is Y is positive because it's on top of that neutral axis divided by I. So you can see that this is negative, this is negative. So this whole equation is going to be positive. So you know straight away your answer is going to be correct because we are establishing just then the top part is going to experiencing tension, and tension is going to cause that whole surface or the fiber on that surface to elongate. So that's going to be positive. So when I do that calculation correctly, I will get the stress at that part of the beam is 106.6 megapascal. Okay, and now we need to go for point B. So I go for point B. Look at point B here. B is actually at exactly the neutral axis. So that is B. So now it's going to be 0 because we said that our neutral axis is our point of reference. It should be 0. So when our YB is equals to 0, this whole term is going to be equals to 0. So we know that actually what happened at the neutral axis of the beam, there's not going to be any stress generated because the fiber on that beam, we assume that it's going to be experiencing no change in length as well at all. So when there's no change in length, there's no strain. And when there's no strain, there's no stress. So that's why at the neutral axis, there's going to be 0 stress. So that solved for bending stress at B. Now we are going to look at bending stress at C. So C, look at its location. It is below that neutral axis. So it's below that neutral axis. What's going to happen? It's experiencing compression. The stress at any location below that neutral axis is going to be experiencing compression stress. Why? It's because the fiber will be experiencing shortening. It's going to experience contraction. So the strain that is going to be caused by contraction or shortening is going to be negative strain. So when there's negative strain, it's going to be causing negative stress as well. So it just means that negative stress is compression. The material is experiencing compression. So that will give us the answer of negative stress. So let's do our calculation. Is it going to be negative? So we are going to look at the distance first. What is the Y here? So the Y will be 120, the location of that C, minus 142.3. So we get negative. So we know that any number here below, we are going to establish that any number below that neutral axis is going to be negative Y. Okay, so bending moment, again, the same. We've already established this for bending moment, negative 100 kilonewton meter from the beginning of the beam towards the end of the beam. It's all going to be constant negative 100. So I plug in my number. I will get, and you can see, this is negative, this is negative. It's going to be positive, but this is negative. So your whole term here is going to be negative. So we know we are safe. Our answer will be negative. So we calculate this, you get negative 22.08 megapascal. So the stress here on that location is negative 22.08 megapascal. Again, that is correct because we as already established the lower part is experiencing compression, so it should be negative. Okay, finally we need point D. So for point D, it is at the base of that materials, of that beam. So that is the distance is at negative 142.3 millimeter from the neutral axis. So our neutral axis is our reference point, and it's going to be negative 142.3 millimeter. So I have, again, the bending moments the same. I do that calculation. This is the y that we calculate here. This is what we have here. And this is our I. When we do that calculation correctly, we will get our answer. The bending stress at that part of the beam, at the lower part of the beam, is experiencing compression stress of 140.89 megapascal. So these negative indicate that it is under compression. All right, so that's for bending stress. All of them from point A, B, C, and D. Any questions that you want to ask me? Ada masalah? Okay, semua okay? All right, let's move on. The last at D, you are asked sketch the bending stress distribution over the depth of the beam. So we know that all the top part is going to experience tension, the lower part is going to experience compression. So we know that. We also know when we derive the equation, it's going to go linearly from 0 at the bending at the neutral axis to the outer fiber. So it's going to go from 0 to for the top part, it's going to go from 0 at the neutral axis, and it's going to go to 106.6 megapascal linearly in linear variation. Whereas for the lower part, it's going to go linear variation as well from 0 to negative 140.89 megapascal. So that is compression. So here, if you draw it like that, it's also correct. So if you draw like that, it's also correct. So that is the stress distribution sketch. And lastly, this is another questions, extra questions that I want to ask. How to strengthen the beam? What do you think you can do to strengthen this beam? So you know that this beam experiencing very high stress at the lower part, the top and the bottom part. What can you do? You think what can you do to strengthen this beam? Just give me one example. No one wants to try? Change the material, go for another materials, use another materials. All right, so if you said you want to change for another materials, what is the characteristic of that material? What that material should have? Higher stiffness. Very good, Ashraf. So it should have higher stiffness. Another thing that we can do composite beam. So we can apply composite beam concept. So instead of I change the whole materials, I can strengthen it by adding a plate of materials that has a higher stiffness on the top or on the top and bottom of this beam. So that's another thing that we can do. Instead of changing the whole materials, we can just bolt or bind another materials on the top and the lower part that has a higher stiffness, higher modulus of elasticity on the top or the bottom or just the bottom of that beam. So you can see that the highest maximum stress is at the bottom part, so we can do that. Okay. All right. So in exam, final exam in second test, bending both are going to be asked. So I want you, I have spent my heart and soul in explaining this to you. I hope everyone understand and can do this. Excellent. All right. All right. Any questions you guys want to ask at this at the end of this question? So we will go have a look at the other questions. So semua faham ya? All everyone understand? Okay, clear. All right, so now let's have a look at this question. I have already given the solution, but I think a lot of you have a problem in understanding it. So the composite beam. So the member here has a brass core bonded to a steel casing. If a coupled moment of 8 kilonewton is applied at its end, determine the maximum bending stress in the member. So here, if you do this, if you do the free body diagram, do it from step 1, you will get that this is also 8 kilonewton meter. And when you do that bending moment, diagram, we will get the bending moment diagram that is positive now. So it's going to be like that, 8 kilonewton meter. In the kitchen, the clock is above the counter is below. So when our point load diagram is going clockwise, in our bending moment, it should go up. Okay, the clock is up. So it's going to go up and it's going to not experience any other concentrated moment. There's no distributed load. So what's going to happen? It's going to go constant. And this is going to go back to 0 because we have this reaction force. So that's exactly what we do just then. So that's why I did not show this. Okay, but now, because we are going to use our stress equation, bending stress is negative my divided by I, and this is for one materials. But we have core that is made of brass, we have the sleeve that is made by steel. So we need to transform this to become one materials when we analyze them. So what we need to do is to use that transformer, the equation that's going to transform this one material to become two materials. Okay. So I divide the Young's modulus of steel divided by the Young's modulus of brass, I get 2. So as I have explained on Friday, what does this 2 means is that the steel is twice as stiff as compared to brass. So if we want to transform brass to steel, if we want to transform steel to brass, we need twice as much materials. So that is what this means. So what will I do? I will, for this case, I will transform this to brass. So you can do it yourself and transform that brass to steel. So what I'm doing is transforming steel to brass. So when you do that, you must maintain the dimension of brass. The brass that you have here, you maintained it. You maintained it. So the one I have in the middle, 100 over 100 millimeter, That is exactly how it is. So now I want to transform steel. The steel here has a dimension of 140 to 140, but it has a hole. It has a hole in the middle of 100 over 100 because it is a sleeve. So I now need to change that to become brass. So it needs twice as much of that size of that sleeve. So what I will do, I will just make it as twice as much. But I'm not going to change what I said in the class the other day. I am not going to change the height because that is going to influence my calculation of that bending stress. Because if I change the height, what's going to happen is that locations from the neutral axis to any part of that beam is going to change as well. So we don't want that. We are just going to change the width. So if I do that correctly, I will transform this sleeve. This is now, you imagine that this now is a sleeve. The sleeve now is getting bigger, okay? This is just formally, this is steel. Now I transform it to brass, so I need twice as much. So you can see, if you do that calculation for the area, you will get that it is twice. Twice if you compare to what you have here. So what I will do, I will just maintain the height. I told you I'll maintain the height, but I will double the length of the hole in the middle. I also double the length of this one. So initially, this one is 100. You can see that this is now 200. So that's 50. This is 50. Okay, so this is now 200. Whereas this one just then is 140. It is now 280. So that's all double, except for the height. Okay, so the width is now double. Okay, so now it becomes one material. You look at it, okay, I know how to solve this now. There's no problem. But for this part, can everyone see how I do it? Okay, Ashraf dia dah try. Dia dah tunjuk dengan saya macam mana dia dah buat. So everyone else must try as well. Okay. Okay. So now this is the shape. The shape of the beam. The shape of the beam. If you imagine, it's become from one materials. It's like the huge rectangle with two holes being drilled into that materials and being taken out. So this is why I have the shape. I divided into three shape, which is the large rectangle, and then I have this two small rectangle here. That two small rectangle sit at that location of that beam next to the original shape of that core material. Okay, so that's going to be drilled out. And this is symmetry. So what we know that this is going to have a neutral axis that is located at this, at 100. This is 100, 50, it's another 2. Yep, so half of that. So this is 70. Oh, 70 millimeter. So that is, you don't have to calculate the neutral axis here because we can find the neutral axis because this dimension, this beam is symmetry. All right, so after that, we just need to find our I. We know that my, I, that is our stress. Stress is equals to my divided by I. So we need to use parallel axis theorem. In this case, we don't have to use parallel axis theorem. We just need to add all of these the area moment of inertia for each of these segment. So we have segment 1, segment 2, segment 3. That's why when you see that my solution, I have said that all the shapes here has the centroid coincide with the centroid of the neutral with the neutral axis. So like for this one, it is here. For this one, this is here. That for the big one, it is there as well. So all of them are on the neutral axis. So we don't need parallel axis theorem. So what we need to find, we need to get the I, the area moment of inertia for shape 1, area moment of inertia for shape 2, and area moment of inertia for shape 3. So area moment of inertia for shape 2 and 3 are the same. So you can just double them. So I will have Ixx is equals to a 12 of this base, that's 280, times height, that's 140 cube, and then minus because this is being drilled out. That's a 12 of the base is 50, the height is 100 cube, and that's going to be times 2 because this and this is the same. And that we will get, it will be equals to 55.7 times 10 to the power of 6 millimeter to the power of 4. So that is our I. So you use the bending stress just then to find for steel. So steel is going to be at the top or the bottom, doesn't matter really. And then you go, we will just do the top part. You can do the top or the bottom. You just put negative or positive because they are symmetric. And for the brass, we take on this part. Because that's where the brass, the maximum for the brass is going to be. That's where it's bonded together. So that's it. You will get for steel, need to transform it back. So for steel, it's going to be times 2 for what you have calculated, and that would be 20.1 megapascal. And for the brass, it's going to be 7.18 megapascal. Okay, so that's it for today. Any questions you want to ask? For question 3 in the, someone asked me the question for question 3 for the tutorial. I'll give you the answer later. Just remind me, I have too much things to do at the moment. Any questions you guys wants to ask? Is this all clear? So no more telling me that this is confusing, okay? Watch this video again when I post it if it's confusing, and watch it over and over until it's embedded in your brain, etched in your brain. The half just now is just, yeah, not half, 1/12, 1/12 for the area moment of inertia, right? Yeah, it's 1/12, not half. Yeah, so this one is actually a 12. Ni kan yang Ashraf kata. Yeah. All right, guys. If there's no more question, please do your exercise. I have given you self-practice question. Do it until you get all the concept. For the self-practice, there's answer there. So you can try it, get the right answer. If you have problem, get back to me. I will try to explain it to you. So we spend about 6 hours on bending. So you have to triple that when you study by yourself. Spend 18 hours on bending. Okay, so we continue with transverse shear on Wednesday. We have 2 hours for we will have 2 hours for lecture, and Friday we will do 1 hour tutorial. If there's no more questions you guys want to ask, I will leave you for today. I'll see you guys on Wednesday. Assalamualaikum, everyone. Bye-bye. Have a very good afternoon, Hang Yi, and all of you. Bye, guys.